This video is an excellent class from the 2023 HVACR Symposium from Joe Henderson. Joe's a great guy. Got to talk to him quite a bit at this symposium. Got to know him. Really great instructor. And this is a class on airflow and airflow diagnostics, which is just an important thing that anybody can learn. Joe's a really down-to-earth guy, a long-time instructor, and I know you're going to enjoy it. Big thanks to everybody who came out and supported the symposium. Big thanks to MeasureQuick and ACCA for being our title sponsors, and everybody else who came out and spoke and who supported it. We have another one coming up very soon, so make sure to go to hvacrschool.com/events to find out more. The 5th annual one is, I would say, right around the corner, but it's not. It's still a ways away. It is in February 2024, but you are going to want to get it on your calendar. And if you haven't gotten your tickets yet, you're going to want to do that ASAP because it is almost sold out as it is. Joe Henderson talking about airflow and airflow diagnostics.
This is airflow measurements and diagnostics. So I'm really excited to be here. I've been following Brian Orr, I've been following Craig and several others for years, Jim Bergman. And when they started doing these symposiums, I was just like, I want to get this symposium, you know, and I never could get there. And so I was so excited that I was able to not only come here and attend it, also to be able to be a presenter. And so I hope you guys are excited too, because I've been traveling across to conventions across the U.S., this is a very unique. There's conventions for distributors. There's conventions for, companies to go out and see all the new jazzy products. And there's conventions for instructors to learn how to train. But for technicians, there's not been a whole lot of them, And so this is fantastic. And for them to make it so affordable, really appreciate it. Glad to be there. So it is an honor, all right, to be here in front of you guys. And also, I am just a little grasshopper walking among these educational giants that are here today. You've got some of the biggest names in the educational industry for HVAC here today. And it is truly amazing. Hopefully you guys will look back and appreciate what you've gotten. And so, being that you don't know who I am, and I'm just a little grasshopper, I thought I would tell you a little bit about who I am. My name is Joey Henderson. I've been doing this for 34 years. I started in the Navy. I was on a nuclear submarine, the USS Greenling. We called it the USS Green Thing, out of Groton, Connecticut. I actually attended nuclear power school right here in Orlando, not right here, but nearby Orlando, Florida, when there was a Navy base in Orlando, Florida, 100 years ago. And had a service company called Comfort Zone. And then later on, I started another service, sold that one, started another one called HVAC Design Services, and a total of 15 years between those two. I've been a carrier and a trained technical rep and trainer for South Carolina. I did that for a total of 15 years between the two. So I was a tech guy and trainer for South Carolina. And then I worked at, when they were building nuclear plants down in up in South Carolina, I was on part of the team there to be an HVAC mechanic for the nuclear power plants. But that project never got completed, so we was there for 3 years and threw pencils up in ceiling tiles and never got anywhere. But if I had got that job, we had a 1,000,000-ton chiller that I was going to be overlooking. It had a few more zeros behind it than I was used to. But hey, they all cool in heat, right? And I've also been an instructor via part-time and now full-time for 30 years. I've been NATE certified. I've been with NATE almost since they started. We got NATE certified there at heat pump installed and service. I was also geothermal NATE certified for quite a while till I let it lapse. I've got HVAC certification, master HVAC. I hold a state mechanical license in South Carolina. I've been an active member of our local Heat and Air Association in South Carolina. I've been educational chair and several other things, put together conventions. And got an associate's degree from Midlands Technical College. I'm also a full-time instructor there. I run the program. And one of our students, I don't know if he's in the class here, but is up here. It's pretty nice to see that. I also run an HVAC consulting company where I do independent presentations like this. I've done it for AHR. I'll be doing it this year. ABM for our SCALT. iConnect training. Went to the Bahamas, did some training there. And also for ESCO. And now finally, I can add to my list that I actually made it to the symposium. And here I am. So I am a die-hard airhead. I love air, and it is a very, very passionate thing for me. I love duct design. I love zoning. And a lot of people don't like zoning because they are not properly designed in the ductwork, okay? But I've got zoning in my house. I've designed many zone systems. I've redesigned many zone systems out there. They work great. I love everything about airflow. Why is it that I care so much about it, and why should you? Whenever I was, first time I had my install business, you know, I came out of the Navy, understood the mechanical side of things. We really didn't study about the airflow side of things, water flow a little bit. And so when I went out there and started installing, I kind of followed what I saw, you know. So when we replaced a unit, if it had a box and ductwork on it, I put a new unit in there with a box and ductwork on it and turned it on. It ran great, right? The handometer said everything was fine. Everybody got a handometer? You use it all the time, right? Okay. All right, so the handometer, super good air. All right, let's go. All right. Had no clue that I was screwing up duct systems all the time. And I was putting in units. Do you think any unit that's rated, of course back then it was 10 and 12 SEER, all right, but any unit, no matter what the SEER rating is, do you think you're getting that when you put that on an existing duct system? Not at all, never, impossible, all right? Now of course, I love the SEER 2 that came out because it exposed what I said was going on all along. See, the first SEER ratings were based on no ductwork. Did y'all know that? That's the reason we're going to SEER 2. No ductwork, no resistance. It was a 0.1 static total. That's no ductwork. The minute you got any static on that duct system, the SEER rating was going down. So I saw this happening, and I took a Manual J, DTNS. Anybody ever take that kind of a class before? All of them, okay? When I took that, my eyes were open, and Manual D just glared at me. Manual D is the standard for duct design, covers all aspects of duct design. And Jim Bergman threw all those manuals up on the screen this morning, you know, and Manual D was in that list. Manual ZR was written later for zoning because of the fact that zone systems were so screwed up due to duct design, not because of the zone system itself. And once I took a hold of Manual D, it changed everything. All my units started working better. All the performance went up. And when I sold that company, and I became a tech rep for Carrier, and that was Carrier and Bryant and Payne back then, and I was a Bryant dealer. I didn't have any troubles with my Bryant system, not one. I didn't have any compressors. I've never lost a single compressor in any unit I ever installed. And I never lost a replacement compressor in any unit of somebody else's that I replaced that compressor in, okay? And it goes back to installation practices. But a lot of it goes back to airflow, okay? And so when I started hearing about people losing compressors and having all these problems with equipment that I installed, I started going out and checking out installs. The number one problem was airflow. Nobody understood it. Nobody, I mean, can you see air? All right. But we can measure things that we can't see. We all know how to use a voltmeter, I hope, all right? If not, finger works good, for, quickie, all right? So, we can measure. We got voltmeters to measure, voltage, right? We got gauges to measure pressure. We got temperature sensors. But how many people got something to measure air up until recently, all right? Not many. Most of the time, how do we measure air? The handometer, right? All right, put it up there. Ooh, got good air. Ooh, got good air, and we're done. We're out of there. Well, it was screwing up a lot of systems. And when I went out there and started redesigning duct systems, explaining to them how it works, all of a sudden, everybody's callbacks started dropping off, light bulbs started going off, and people that paid, what, $10, $12, $14,000 for systems were actually getting more what they paid for. Think about it. A customer, if I paid $1,000 for something, do I want somebody to say, hey, it works pretty good? You'd say, oh, thanks. No. I want that thing to work perfect if I pay $1,000 for something. What if you paid $12,000 for something? And they said, pretty good. Came on, got good airflow, bye, see ya. What does a homeowner assume that you've already done? A thorough job of checking electrical, refrigerant, and airflow, right? Did we? Most time we did it. Why didn't we do it? Didn't know how. Didn't know how do you measure airflow? Right? We don't know. I taught all across tech schools as a Carrier rep. The number one subject that was the weakest on teaching was airflow. Most of the time, even the instructors didn't really know much. And everybody that had a ductulator, it only needed one setting. 0.1, that was it. And that got everybody going, right? Okay, that was wrong too, all right? So you should care a lot about this because in the end, if you don't get it right, if you don't check it, you don't know what you're looking at, you just robbed a customer. You just took $12,000, $14,000 out of their pocket. You don't think that way. I know you didn't wake up thinking that way, but that's what we end up doing, right? You're like a mechanic that just kind of halfway puts some screws back in the starter, and you walk out of there, what happens, right? Same thing. So let's talk about how to do it. First of all, what happens up inside of a duct system? This is just a representation right here of how the air flows through the duct. We've got two kind of pressures that we work up. Okay, we got velocity pressure and we got static pressure. The thing that I want to talk a lot about is static pressure today. I'm not talking about duct design as far as how to use a ductulator and all that. I want to talk to you about what happens inside that duct. Now, when I talk to customers, I explain that the fan motor here, that's just like your heart. What your heart doing is pumping blood through your system, right? It's circulating blood all through the system. That heart's just moving. Well, that fan motor is like the heart of this system. Guess what the ductwork is? Our arteries, right? And then the air is like the blood flowing through our arteries. If you've got restricted arteries, what does it do to you? High blood pressure. What's the silent killer? Anybody ever heard that called? High blood pressure is a silent killer. You can have high blood pressure right now and not even know it and die of a heart attack. Get a stroke. And you had no symptoms, no signs. That's what happens with a lot of times with airflow. We think just because this thing's turning and this thing's running, we got good airflow, right? I mean, we figure everything came on, so it's fine. But it's not. And it's a lot to do with this right here. So when you look at these lines right here, this is the air moving through the duct, and air is always trying to expand. It's always pushing out, right? You blow up a balloon, what does it do? Right? All right, well, the metal ductwork can't do that, can it? So the air is pushing against that ductwork, and that's creating resistance. Okay, so ductwork's got resistance going through it all the time. And these arrows are pointing that the resistance is on the outside edges of the duct. So this is called our static pressure. It's the pressure that's pushing against the outside edge of the duct. Now what's going through the center here is velocity, okay? And a lot of times that's what we're dealing with on this motor. This motor can only push and pull so much air against so much resistance, right? Okay? So if you got a car, got a little beep beep 4-cylinder car, right? Okay? It can only go so fast on a road, especially when it starts going uphill. What about if you had a 6-cylinder car? Would it have more horsepower to do the job? Right? What about an 8-cylinder? Even better. Okay? Same thing. These motors are rated to only handle so much load, static pressure against them. And so what we've got to do is we've got to make sure that that motor is operating in its proper static. How do we know that? How do we measure it? Well, this is the standard way of measuring it. Now, we've also got the air grid out there now, right? And that'll measure total airflow at the unit. What I'm looking for is I want to measure what the static is to get a balance of static pressure so that we got smooth, quiet return air and a good throw of supply air, okay? And I want to know where my problems are. With the static pressure probe, I can actually start hunting for problems, okay? All right, got that word from Rob Falk, all right? Hunting for problems with a static pressure. So, you know, we've got these kits right here. We've got, you know, different kinds of manometers, but you got to have a manometer to measure static pressure, okay? Anybody ever remember this guy? All right, okay? Had to have a level, had to zero it out. It was perfect as long as you mount it on a wall, all right? But these days, this is about where we're going. We're going on the digital side of things. And we've got to have what's called a static pressure tip. Anybody know about a static pressure tip? Good deal, all right? Now, the most accurate way that I have learned to use these is you want to be sure that you point this tip into the airflow. Because what happens, you see it's a bullet. There's no hole right there. That's totally closed off. So when you got that tip and it's pointing to the airstream, here comes the air, and when it hits it, it expands around it, okay? So what does it create on the outside edges of it? It's static pressure. And that's what these little holes right here are measuring, is the static pressure. So you always want to point it into the airflow. That's really important. If you turn it the other way, you'll still get a reading, but I've seen it go off a little bit. So I always recommend you go this way. And the one thing this is not, it's not a pitot tube. Okay? Pitot tube has a hole in the center and another line to it so it can read static and velocity and give you CFMs. So this is just a static tip. And they're out there, and you need to have one. Okay? Another way you can do it, if you don't have a static tip, and I've tested this in the field, is you can take a straight piece of tubing, and if you run it at a 45-degree angle with the airflow, this will create a static reading in that tube, and that'll almost get you almost as accurate as a static tip. So if you don't have a static tip, you got a little straight tube. So, you've got your little flexible rubber tube. That might work. Just make sure that it's at that angle and check it out. And the next question is, where do you take it? Well, you want to make sure that you are catching every single thing that motor's having to pull and push against. Now, this right here is just a nice little illustration, right? Little straight duct. Straight duct coming in, straight duct coming out. But what do we know happens to this right here? Right? That's it. There's our supply duct right there, the whole thing. And then what do? Either we come off left and right with big 14, 16-inch hard pipe duct, bullhead T, right? Or we come off of with what? About 15 flex runs. All right? I call it the Chinese water dragon. All right? All in the house. All right? And this motor cannot push against all that stuff. I think we know that. We just don't want to believe it, but it's true. So what happens is we start taking our static pressure readings. Well, you get over here, and the evaporator coil in the air handler has already been configured into the static pressure reading of that motor. That motor's already been designed for it, okay? Now, most of them say a dry coil, and where I'm from, that does not exist in the summer. South Carolina, there is no dry coil in South Carolina, all right? They're all wet. I think they're wet before we even start them up, okay? All right? But you want to take it, if it's got a filter right here, you want to take it after that filter. If you take it over here in a little more convenient spot, but they got a filter, guess what? That right there is more restriction, and it can be a heck of a lot of restriction. A furnace, a pleated filter, we call them furnace killers, all right? All right, you got to be careful. Filter pressure drops are massive. And if you're not measuring after that filter, you're going to get wrong readings. Now, here's the other thing, too, is that in order to get correct airflow readings, you've got to have straight air, all right? I'll give you a new party word so you can sound real smart. Okay, it's laminar airflow. Laminar airflow. All right, so next time you're at a party, you go, I wonder if you got a laminar airflow in that bit right there. All right, laminar airflow. It's got to be straight. And if you look at the readings, before you can get straight duct airflow out of the duct, you've really got to have 3 to 5 feet of straight duct before you do anything to it. No changes. Okay. So when you do a bullhead T, you got a plenum box here that may be 24 inches long, and you got 2 18-inch runs off of it, or 2 16s or 14, whatever you got. Here's what happens, is the air comes out of that blower, and it's whirling around coming out of there, okay? And it's coming out, and it hits that box. And where does it go? Back this way. And it just creates this turbulence effect. You can't get airflow reading in a turbulent box, because it's like little eddies. Like the water comes off a waterfall, all right? Comes down, at the bottom, what is it? It's a mess, all right? Water's just swirling everywhere. They got dead spots. They got areas where the water doesn't move at all. And then finally, what happens when you look way down the waterway? It smooths back out, okay? Well, that's what you got to let airflow do before you get an accurate reading. You've got to let it straighten out. So what I started finding is that guys I was happy if they were taking static pressure readings. That was a great thing, all right? But they weren't getting accurate readings. They were reading low static. I thought they were in good shape. All it was is dead air. It's dead air. And if you've got too many turns too close to the outlet or the inlet, even the inlet counts. So when you come right here to, returns right here in the back of this box, it creates turbulence there. What we get is called system effect. That's a term, system effect. Too many turns, too many twists, too close to the unit, and you get so much turbulence, no reading will work. You can throw your static pressure readings in the garbage. They're not accurate. It's got to be straight air. So there is another way to see if your motor is overworking, to see if it's producing. You can take an amp draw of the motor itself, okay? An amp draw of the motor. What about a PSC motor? If you got a PSC motor, what do you think if it's pulling too much load on it, too much static? What's it going to do? Yep. The amp goes up because it's not moving that much air. What do you think? It's going to hunt around? Oh, the amperage is? Okay. What about you? What do you think? Hold on. You want me to say it, don't you? I can't say it. All right. All right. You're not gonna, a lot of people don't really understand this. So if you've got a PSC motor, and a PSC motor has a fixed horsepower, right? Okay? I mean, you got a couple of speed taps, but you're on one of those speed taps. If you've got too much static, does it move more air or less air? Somebody answer. Less, right? It moves less air. Is that more work or less work for that motor? Let's see, 50-50. All right, more, less, all right? If it's moving less air, it's less work. So does it pull more amps or less amps than it's rated? Less. Yeah. So it's a dead giveaway. Before you even pull out all the bat gear, okay, you just turn the fan on, go up to the disconnect, make sure the heat strips aren't running, all right? Look at what the rated amperage is on that, or rated amps in that motor, and take an amperage reading on the motor. If it's pulling less than rated amps, it's moving less airflow, period. Now you can go start finding out why. If it's pulling full load amps, PSC motor now, with a capacitor, right? We know we're loaded up. We're moving the correct airflow, right? It doesn't mean that we're a balanced static duct system. That's the next thing I want to talk about. Now, let's talk about a ECM motor. All right, how many types of ECM motors we got? What you think? Tell me. You don't count. He's my other instructor. X13. All right, what else? Constant speed. All right, so the X13 is the constant torque, right? And then the other one is Constant-CFM, okay? Now, anybody remember the old term, variable speed? All right, I grew up with that one, okay, because there was no constant torque that we knew of at the time, all right? But now that we got the two types, a lot of people think that an X13 works just like a variable speed motor because they look kind of similar, right? Okay, they're both three-phase DC wound motors. They both have a module on the back of them, all right? Biggest difference is Constant-CFM has what? 5,000 wires going inside of it, right? Okay? Constant, and the constant torque has less wires. But a constant torque is a high-efficient motor. But does it have any more airflow capability than a PSC motor? Yes, no. What do you think? Oh, no. All right. Who does know? Somebody tell me. Technician. Somebody. Nobody wants to answer. All right. It has the same airflow capabilities as a PSC motor on average. It just does it more efficiently. But the minute it hits its static limit, around a 0.5, guess what it starts doing? Losing airflow, okay? Now, it'll start losing airflow, but not near as fast. Is my time over so far? Oh, I know time flies when you're having fun, but really, all right? So what happens to the amp draw of a X13? Okay, it actually bumps up just a little bit at first because it's holding on with that constant torque capability, all right? And then it'll start gradually dropping off as well. So it's not as immediate as a PSC. It has a little bit more of a hang time after it gets past its limit before it starts dropping off. Now, what about a Constant-CFM? You go over there and you pull an amp draw on a Constant-CFM. You do not want to see max amps on that bad boy. All right? If it's pulling max amps, you can definitely take the sear and throw it in the tank because it ain't efficient now. Is it giving you the right airflow? As long as it's at, Now remember, you can go past the static of a constant CFM. It's not a guarantee. But if it's pulling max amps, that joker's ramped up like a hurricane, all right? You'll be pulling the 3-year-old off the return, okay? They'll be like poltergeist, help me, okay? All right? It'll sound like it's raining in the vents. Everybody ever heard that when one's ramped up like a hurricane? All right? I'll walk in a bonus room and we'll be like, dang, I'm ready for the vents just to fly off the daggum ceiling, all right? And of course, whose problem is it? It's that darn variable speed, right? That's the problem. Nope, it's too high a static, okay? So you can quickly, if you've got a duct system that's not the straight air, you can do an amp draw just to prove to yourself whether it's really moving the right airflow or not, okay? So a PSC, you want to see it at full load amps, an X13 full load amps, a constant CFM, you want to see it about half to 3/4, all right? Now, I've been saying this for years and years and years, and I'm real good friends with Chris Mahaly. Hope I said that last name right. And I verified that. He gave me his green light on that discussion, all right? Now, if you're moving max amps on a constant CFM, are you still moving the right airflow? Most likely, yeah, but at too much money, and you have no room when coils get dirty. Okay, so you can do this, use your static tips, but be sure that you've got straight airflow. So here's your PSC motor. Most of them are going to be rated at a maximum of 0.5. Has anybody looked at a blower table and seen them rated at 0.3? I promise you, there are some air handlers out there, and I used to work in the industry, in the manufacturing side of things. The way they could get you an inexpensive air handler is to give you a very low horsepower blower motor, okay? And you go look at them tables, 0.3 was where you got your airflow. Now, I could go to 0.5, but you might not be getting 800 CFMs, you might be getting 600 CFMs, okay? Brand new, right off the bat. So be sure you look at your blower tables. But on average, 0.5. Now, that also includes X13s, like I said before. They're not a variable speed motor. They look like one, but they're not. Now here's your variable speed. Now variable speed, depending on the manufacturer, can go from 0.8 to 1 inch of static. Now, if you're not sure what in the world good static is, because like I go get my blood pressure taken, right? And they, when they get done, they say, oh, okay, well, yours is such and such over such and such, right? I have no idea. Is that good? And I always ask them, is that good? Is that bad? Am I going to die? What is it, you know? And they would say, good. Oh, it's a little high. Well, it's a little low. It's okay, all right, you know? And, you know, if I go back the next 3 times, it's usually different stories, right? But what you're looking for on duct system static depends on the motor, okay? And we'll talk about that in a minute. So what are you looking for, all right? Yes, please, question. So at what amps do you start becoming concerned that there's a low airflow problem? I say that right? Okay, all right. So it all depends on the motor. If it's a PSC motor, gotcha. So if it's a PSC motor, you know, you're going to be looking within 10% of its rated amps would be a good number to look at, okay? All right, so I think that's what they're looking for on a PSC when you start having trouble. I like to see it, and remember, your meters are going to read differently depending on the quality of your meter, depending on the battery of the meter. I got where I was changing batteries every season. When spring came, I changed batteries and everything. When fall came, I changed batteries and everything. I mean, I didn't care. And 2 reasons. One, the weaker your battery gets, it can get inaccurate, and you don't know it, okay? Secondly, if you forget and you got an instrument you don't use a whole lot, what happens to that battery after a while? Corroded. I've lost a $350 meter because I had a $2 corroded battery in that darn thing, all right? And trust me, I had emery board and I had Q-tips and everything else. Gone, all right? From then on, buddy, I changed batteries like nobody's business. I just kept a whole pack of them, okay? So, and there's nothing worse when you're out in the middle of nowhere and the battery goes out and you ain't got no replacements, no backup, okay? All right. So, thank you. Hope that answered the question. All right, so on non-constant CFM motors, okay, PSC and X13, operating static, startup static, in my opinion, based on what I've seen and in my own duct designs when I've measured them myself, you want to start at about a 0.3. Don't get a 0.5 and go, woohoo, all right? That means you're already maxed out. If you got a 0.5, you ain't got no room for a dirty filter. You ain't got no room for dirty coil. That's the best that unit will ever be that day. And after that, it starts collecting dirt, starts collecting dust, and it starts getting dirty. And that, if you start at a 0.5, you got nowhere to go. You're going to start losing airflow from the minute you started it up. And you'll never get it back in most cases, okay? So 0.3 is what you're looking for. So why? Gives you a good thing. So 0.3, no more. Now, when you look at the supply plus the return, when you have a manometer, what you hook up on the return is the negative, is the minus sign on your manometer. What you put on the supply side is the positive sign on the manometer. But the two you add together. It's not a subtraction, okay? It's not like the supply static is, say, 0.2, and your return static would be 0.1, which would be a lovely reading, by the way, all right? You don't say 0.2 minus 0.1, there's my total static. You add the two numbers together. The minus sign just tells you to put it on the return side, and the plus side just tells you to put it on the supply side. I wish somebody would have told me that when I was turning it out, all right? That's how it works. I had the darn Magna Helix. I was like, well, which one goes where? You know, did everybody get a new one and get the instructions out of the darn thing? Well, there was none, all right? And there was no Google to go find out what it was supposed to do, all right? Dadgummit, all right? So, you want to be sure that when you measure supply and return, you measure them separately. Don't measure them together, because what if out of that 0.3, all 0.3 was on the return? You don't want all your static built up on the return. What's that a good indicator of? A restricted return, all right? And now your static on the supply side is probably nothing, all right? Because it's conservation of energy. If it's all on the left, there ain't nothing happening on the right side, okay? So you've got to balance it out. You want the return static to be less than the supply static, okay? You want a balance there. So in an ideal setting, what I'd be looking for is about a 0.1 on the return and about a 0.2 on the supply, okay? If you've got that balance, which you can by duct design, then you'll get a good airflow read. Yes, sir?
You say measure them separately, one at a time?
Yeah, I never have two hoses in my duct system because I don't know where the static is. So let's say you read the 0.5, you know, and you go, well, at least I got that, all right? Yeah, but if 0.4 is on the return, you've got an undersized return, all right? Because remember, overall, you may be getting the airflow across the coil to get capacity, but your distribution, your duct performance is going to kill it. And if you've got any duct leakage on the return, if you got all your static on the return side, what are you going to be doing? You're going to be sucking in everything through every single crevice on that return duct. I've seen a 10-degree drop in a wintertime in a crawl space from the return air entering the return grill through a single piece of flex. It was no longer than 20 feet, went straight into the ductwork, and we were getting a 10-degree drop of temperature before it hit the furnace, okay? We weren't getting a good performance. I was like, where is this going on? I promise you, it was an inch gap in the return pan. But why was it sucking so much air through there? Because that darn flex was like all the static. Okay? Yes, sir?
Why do you want to have the static pressures different between wires?
Good question. The question is why would I want them different rather than say what? Exactly equal? All right? The reason I would want the static lower on the return is because it's slower airflow. I want to get it low and slow, all right? Just like I like to cook, all right? I love cooking, all right? So I like to do a smoke cooker. But you want that air to come at a slower velocity to keep it quiet, okay? And so that way, if you keep the static down, you can ensure that it's going to be quieter. If you keep the static up on the supply, then you get a little bit more velocity and a better throw out of the vents. That is my reasoning for it, okay? And by the way, I came out with that rule just from field measurements. I haven't seen that in a thing. I don't even know if NCI teaches that or not. Do they do that, sir? No, they don't teach that, he said, but they will now. So there we go. There you go. All right. All right. So now, what about a constant CFM? All right. Constant CFM gives you a little bit more leeway. But if you started out about a 0.35 to 0.5 total with the same rule, supply a little bit higher than the return, it's going to be pulling about half or a little bit more rated amp draw, which means it's going to be running sufficiency. I don't know if, when I worked for Trane actually put the wattage of the Constant-CFM motor along with the static pressure reading. And the reason for that is that the real SEER rating is what? How many BTUs per watt you get, all right? And the higher that CFM, Constant-CFM had to ramp up to get that airflow, the more money it costs, and it started eating into the efficiency, okay? So you want to get that balance. Well, if you started off at about a 0.35 to 0.5, and you can go up here, no problem, then now you've got room for dirt with that one. So it keeps it quiet, and it keeps it efficient, okay? The higher it has to ramp up, the more money it's going to cost. Now, let's talk about how a Constant-CFM motor works in general, okay? It's like a cruise control in your car, okay? So, you know, David over here, when he like sets his cruise control at 90, you know, when he's running late, you set your cruise control in your car, you're going down a flat interstate, everything's fine, right? But the minute you go uphill, right, what does it do? Does it speed up? It does? I thought it was cruise control. I thought it kept the speed constant. The engine increases, right? The RPM of the engine increases. We're maintaining that 70. It's tapping into the available horsepower to do it. Now, if I'm in what I used to have, a little 4-cylinder Ford Ranger, all right, you know, the minute I went uphill, I don't care, all right? That thing's to the floor, and I'm still, I ain't going nowhere, all right? Because all my horsepower was used up just to go down the flat part of the street, all right? The minute I went uphill, I had no horsepower. Same thing with a Constant-CFM. It's like that beast, okay? It's like that big diesel. You just crank that thing up, or you back it out. And if you put this up against maximum static, that'd be like you having to stomp that ginormous diesel truck just to get out of the driveway. And you had to keep it that way everywhere you went. What do you think the gas mileage would be on that thing, all right? All right, so, but that's not the case, right? You've got available horsepower. So when you're in a bigger engine, you got it on that cruise control, and you go up that hill, what does it do? Ramps up, it taps into the available horsepower to maintain constant speed. Well, that's how a variable speed motor works, okay? The variable speed motor reads the resistance of the ductwork, and it speeds up to overcome it. So you want to be sure that you're keeping that at about a 0.35 to 0.5. So here's some key points to keep the static pressure down, okay? Is you want to keep the trunk line as straight as possible. Straight as possible. Now, if you've got to Y off to the left and the right, 3 to 5 feet. You know those supply ducts that you take like 1 foot off the air handler, right? Because you got that supply duct like right there, all right, you know? It sure is convenient. Supply, boot, done, all right? But I promise you, you're creating a lot of turbulence, not only for that one, I've seen it actually pull, you know, anybody ever did the highly technical tissue paper test? All right? All right? All right? Hold it up there. All right, well, I put this, that's how you go check returns, right? Foop, okay, it's working. It sucked in my thing, you know? All right? I was really worried when I put it on there, went, I was like, oh, okay, we're not working. All right? So, you know, but you go over there to the supply, all right, and you do a little tissue test. Well, I had one job, and I mean, I was telling, I said, it's too close here. And I was like, it's kind of working, you know? Well, I put that tissue in there, and the tissue went, foop, foop, foop. The air was turbulating so bad in there, it was sucking air in and pushing air out, about that far off the grill, okay? So it creates a lot of problems. So you want to keep that straight duct. If you'll get 3 to 5 feet of straight duct on the return as well as the supply, I promise you, you'll get better airflow performance, period, just doing that, okay? The other thing is, and one of my mottos is you can make small changes and get big results. And the small changes are with the duct fittings, okay? Now, straight supply runs and low-loss duct fittings. So you want to pull your flex duct or run your pipe, right? Well, hard pipe you can run straight because it's hard pipe, right? But flex, you want to pull that stuff straight and tight. I would reach in and grab the, not the outside. Outside looks beautiful, you know, but it's not like an extra 6 feet of flex up inside that thing, all right? So you want to reach inside there and grab that inner vinyl lining. What I'd do is I'd hook it up on one end, and I would reach and I would grab that vinyl and I would try to pull it off the boot. And I'd pull it straight and tight. In Hart and Cooley and the other manufacturers, the way they get their airflow ratings through their flex duct is they put it on a machine and they go, all right, pull it straight and tight, all right? And then they measure and they say, ha, I got good airflow. Well, is that how it happens in the field? Heck no, all right, running around and everything, This is a good little illustration of how the air flows through a duct. I don't have any money to do all that high dollar animation, so here we go. So here comes air flying through the ductwork here on the return. Here's something that's really, really interesting, that's pretty neat, is that if you can see right there, all right, as the air takes this turn, it creates a little bank of air right up in here, and it actually creates a smooth turn. So the outside turn curves all by itself, okay? It's the inside turn that kills you, because all the air, 5 minutes, all the air, all right, so y'all got all that? All right, air turns really tight right there, creates a turbulence. Let me cut to the chase here. You want to miter the inside turn, not the outside turn. Miter the inside turn, and it will cut the static restriction by at least a third or a half, okay? And then up here, you want to be sure that if you come up here with our straight duct, don't do a bullhead T, unless you got turning vanes, all right? But if you ain't got turning vanes, use a Y fitting. Use a squared around. Don't do the cap with a hole in the center of it. I ain't got time to explain all the problems with that, all right? If I could ride around with a big sign on the van or walk around with a big sign downtown, all right, I would say squared arounds, round Ys, okay? Hard elbows when you make a turn. Every flex run, I had 2 elbows, all right? One at the takeoff and one at the boot, all right? Now, if the takeoff was straight up to the boot, okay, I didn't need elbow there. But the minute I got to angle it, I put a hard elbow in there. If you do those things, I swear it'll make so much difference. And the last thing is you want to up, and I ain't got time to show you this how this works, but if where you used to run a 6-inch flex, run an 8. Where you used to run an 8, run a 10. And I promise you, you will create a lot less restriction. And I went to where I had no 6-inch runs in my duct systems. All right? It's because what happens when you get in the field? It's not straight and tight. It's going to have some sags and turns. With that little extra flex duct sizing will help overcome that, okay? So, just a little tidbit there. All right, I want to go, okay, don't do that. All right, all right, don't do that, don't do that, and don't do that. Now, let's look at some problems here. Okay, 5-ton air handler. I wish I could tell you about the whole job. I took that picture. All right, how about that one? Yeah. I didn't take that picture, all right? I thought that was a good one. Just wanted you to see one good one, all right? Looks like a big stick bug in the attic, all right? See any problems there? All right. Problem with that one's no flash. All right. How about that one? Oh, yeah. And then, of course, we got a zoning duct on it. And they couldn't figure out, this is at a $1 million home. No, $1 million home. All right. This was a 5-ton air handler with a 2-foot flex box. Oh, it was a mess. All right. By the way, not only does it cause airflow issues, when you get all that high static, like I told you about on the return, your drain lines won't work. They'll hold water the whole time they're running. And I went on a lot of jobs where it was me, the contractor, a lawyer, the homeowner, and the installer when I was a tech rep. And it was because of a darn drain line not draining. When they opened up the unit, guess what was all up in there 2-3 years later? That big word, right? We can't say that really bad looking stuff, all right? So, yeah. So it was a problem. Lawsuits occurred. How about that one? Yay. I like to say all the time. All right. That was nice. Hey, but they used 10-gauge wire at least. That was nice. All right. All right. How about that one? Silicone fixes everything. If you ain't got ductwork, deal with silicone. Literally, it's a Nike box. All right. All right. How many ding, 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 ding. All kinds of problems with that one. And poor old Lacey, you got too small ductwork on that one. All right. All right. Like that one? Yeah. All right. Yeah. That's good. Huh? Oh, I love this one here. This is one of the jobs I went on. Big old pleated filter, cut off half of it. Okay. All right. How about this one? Anybody ever watch Teletubbies? I did when I was there. Okay, never mind. But that looked like Nunu. Look like a vacuum cleaner. Kinked a little bit? Maybe so. I used to go through all the exercises on how to fix that. Too late. All right. No crawl space, no attic. Who cares? All right. Oh, how about that one? Hey, they won't sweat. Promise you that, okay? All right. How about that one? No. What are people thinking? All right, so now, I took this one. All right, this is on top of a hotel. They've been losing multiple compressors. Oh, I wonder why. All right, so how about this? 7.5 ton package unit. Guess what those are? 14-inch flex duct. Wow. All right. All right. How about that one? Yeah. Okay, to their defense, that was a temporary unit sitting out there. All right, but it looked really wild. Okay, it's my favorite. That's been around for 1,000 years. Anybody ever seen that picture before? All right, okay. So we always call it that the lowest bidder. And today I heard a new term from Jim Bergman. That's called two-stage equipment. That's exactly right. Okay, here's some things right out of Manual D, which do straight and tight. Don't do the Chinese water dragon. All right, use hard elbows. Don't kink that off to the side. You might think, oh, no big deal. That creates a lot of turbulence. Straight and tight, straight and tight. So there you go. By the way, this presentation is on a PDF for you guys. And here's the duct fittings. Wish I could go over that some more. But duct fittings will kill you. That one torpedo boot everybody loves to use, that's worth 50 feet of duct restriction. 50 feet. All right, that's a ton of duct restriction. Don't do it. Yummy. Used to fix those a lot. All right. Now, how about these? Duct board. You might use duct board? God bless you. All right, so now, here we go. Just got to do it right. That's the correct Y duct board, not that one, okay? All right. Now, who can spot the good, better, and best other than the fact that it's labeled? Okay, all right. This is bad because we got these hard inside turns. This is better because we got inside turns that are curved. This is better because we got turning vanes. This is the best because it's inside, all top and bottom. You throw some turning vanes in there and who knows what static drop will be on that thing. All right, so, but this is the best way to go, if at all possible, or you got turning vanes. Bullhead teeth, bad, bad, bad. All right. So here you go. These are rough numbers, depending on how close they are, but roughly that's about a 5 to 10 foot restriction, and that's a 10 foot restriction compared to 50 feet. Okay. All these add up. Believe it or not, your takeoff's are 35 feet of restriction. 35 feet. Here's an underlying problem that a lot of people don't even think about. Duct systems all together, and we got poor airflow. We're checking everything. Everything. What the heck, you know? Well, has anybody, you ain't got to raise your hand. Anybody ever done that before? All right. You know, kind of bad. I'll tell you what, that causes airflow problems. Stop, he said. All right, and there's a good one. Okay, yay, operation first. Yay, have a good day. Right.
Big thanks to Joe Henderson for doing this. Much appreciated. And once again, thanks to everybody who came out to the symposium. We look forward to seeing you again in February 2024.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.